Hello, and welcome to Lesson 15 of this Introduction to Differential Equations with Wolfram U. In this lesson, we will discuss some physical applications of second-order differential equations. This will include mechanical oscillations, applying damping and driving forces, and simple harmonic motion in electric circuits. Before we get to the applications, let's take a look at an overview of mechanical oscillations and simple harmonic motion. In the first lesson of this course, we saw that differential equations can model a variety of physical phenomena spanning many fields from physics, engineering, economics, biology, and many others. Second-order linear equations are of particular importance because they can be used to model mechanical vibrations and oscillations, such as the motion of a mass oscillating on a spring. To see how second-order equations relate to mechanical oscillations, recall that Newton's second law states that the acceleration of a body, or the second derivative of its position, is directly proportional to the sum of the forces applied. This statement about Newton's second law is given here as an equation. We can see that what Newton was describing was a second-order, non-homogeneous differential equation. An example of simple harmonic motion is shown in the animation here, which is displaying the motion of a mass hanging from a spring. The spring is initially stretched. When released, the mass displays simple harmonic motion, which is the oscillatory motion seen in the plot showing the position of the mass over time. We will see in this lesson that the model described by Newton is well equipped to describe a variety of different harmonic oscillations. This includes simple harmonic motion, which we saw in the animation on the previous slide, as well as damped oscillations and forced oscillations. Consider the model of a mass hanging from a spring. When the mass is at rest and attached to the spring is lengthened by a length L relative to when the mass is not attached to the spring. In this situation, there are two forces acting on the mass. One is the gravitational force, pulling the object down, while the other is the force of the spring holding the object up. When the object is at rest, the acceleration of the mass is zero, so the sum of the forces must be zero. This is represented by an equation here. The mg term represents the force of gravity, while the F sub s term represents the force of the spring. When the mass is displaced, we know from Newton's second law that the mass times the acceleration must equal the sum of the forces, in this case the gravitational force and the force of the spring. The force of the spring becomes larger as the spring is stretched, so we can say that the force is proportional to the elongation of the spring. This is written as an equation here, where K is the spring constant specific to the spring and defines how much force is added as the spring stretches. L is the amount the spring is elongated by relative to when the mass is not attached to the spring, and y of t describes the displacement from this equilibrium point. With this definition for the force of the spring, we can write Newton's second law as this. Note that mg minus kl is zero. This is by definition, since the force of the spring when elongated from its unstretched point by a length L is equal to the force of gravity on the object. Canceling out these terms, we get a second-order homogeneous differential equation to describe the simple harmonic motion of the mass on a spring. Consider an object weighing 2 pounds hanging from a spring. The object stretches the spring by 4 inches when the mass is at rest. Suppose that the object is then displaced an additional 2 inches downward, then released. We want to set up and solve the differential equation that represents this physical situation, then plot the motion of the spring over time. We have seen that the model of an oscillating mass on a spring can be represented by this second-order differential equation. In order to calculate and plot the motion of the object over time, we need to get numerical values for the object's mass and the spring constant. First, let's solve for the spring constant using the equation for the force of a spring. When the object is at rest, y of t is zero, and the force of the spring is equal in magnitude but opposite in direction to the force of gravity. Therefore, we find that mg is equal to kl. To find k, we need to define the mass of the object. We are given the weight of the object in the problem. To get the mass, recall that the weight is defined as the mass times the acceleration due to gravity. You may not know the acceleration due to gravity in the imperial system off the top of your head, or you may not want to go through the work of converting the SI units yourself, but luckily you don't need to. The Wolfram language can handle these units for you. To define the mass, simply define the 2 pounds in the numerator and divide by the acceleration due to gravity. You can get the acceleration due to gravity by pressing Ctrl and equal on the keyboard to open the inline freeform input. You can then type acceleration due to gravity in order to get the small g. Now with the mass defined, we can calculate k from the equation mg over L. We can see in the statement of the problem that the object is initially displaced 2 inches downward. Therefore, this is an initial value problem. In the differential equation, we are dividing by m so that the second-order derivative term has no coefficient. The initial displacement is given as an initial condition on the value of y of t at t equals 0, while the first derivative at t equals 0 is 0, since the velocity of the object is 0 the moment it is initially released. Now that we have the equation and all of the quantities in it defined, we can solve it with d-solve value. First, calculate the quantity k over m in the differential equation. Substitute this value into the differential equation and take the magnitude of k over m to cancel the units. We can then insert the equation and initial conditions in the d-solve value and solve the equation. We see that the solution is given in terms of a cosine, which makes sense because this should represent simple harmonic motion. Let's visualize y of t, which gives the position of the object over time. One can imagine how the oscillatory motion shown in the plot represents an object oscillating on a spring. In the previous example, there was no damping or frictional forces such as air resistance, so the solution to the model would have the mass oscillate with the same amplitude forever. Here we will consider simple harmonic motion with damping. Consider an object that weighs 1 pound and stretches a spring by 6 inches when hung from it. Suppose the mass is displaced an additional 2 inches then released. The force of air resistance is proportional to the velocity with a proportionality constant of 1 over 100. Our goal is to find the differential equation and initial conditions for this initial value problem, solve that model, and plot the motion of the object over time. We are first going to assume that the air resistance always acts in the opposite direction of the object's velocity, so we can write the force of air resistance in this form here. Now, the differential equation for the motion of the mass has this additional term in it. We can calculate the value for m in the same way we did as the previous example, and similarly for k. The proportionality constant to account for air resistance was given to be 1 over 100. Substituting these values into the differential equation and taking the magnitude of the quantities to cancel the units gives an equation for the motion over time. Now that we have the equation defined, we can solve it with d-solve value. However, we first need to define the initial conditions for this initial value problem. From the statement of the problem, we know that the spring is initially displaced 2 inches or 2 over 12 feet downward. Like in the previous problem, the initial velocity of the object is 0. All that now remains is to find the solution with d-solve value. The solution looks complicated because of all the numerical values, so let's plot the solution to visualize the motion of the mass over time. We can see that the oscillations dampen gradually, which is to be expected when an oscillating object encounters air resistance, but the oscillatory motion seen in the simple harmonic motion example is still observed in the solution. Let's consider now the case where the object attached to the spring experiences both air resistance and an external driving force. The object weighs 2 pounds and stretches the spring by 3 inches. The object is then displaced another 3 inches and released. The air resistance is proportional to the velocity with a proportionality constant of 1 over 50. There is also an external driving force acting on the object, which is a force measured by 1 over 10 sine of x. Let's formulate the initial value problem associated with this physical situation, then solve and plot the solution. An external driving force acting on the object that does not depend on the object's position, velocity, or other variations of the spring will appear in the differential equation as a non-homogeneous term. In order to simplify the discussion, we will approximate the acceleration due to gravity as 32 feet per second and cancel the units right away. We can now define the mass and the spring constant. The proportionality constant is given in the statement of the problem to be 1 over 50. Substituting these quantities into the equation and including the external force as a non-homogeneous term gives us the differential equation describing the system. The problem states that the spring is initially displaced 3 inches, or 3 over 12 feet downward. The initial velocity is again assumed to be 0. We now have everything we need, so all that remains is to find the solution using d-sol value. The solution is complicated, so it is hard to see the behavior from the equations, but we can easily plot the solution over time. We can see that the amplitude of the oscillations quickly dampens over time due to the air resistance, while the motion of the mass at large times becomes dominated by the external driving force. It is quite fascinating that the model for an oscillating mass on a spring also represents the flow of electric current in an RLC circuit. Here is a diagram for the RLC circuit, which consists of a resistor indicated by the R in the diagram, an inductor labeled by the L, and a capacitor labeled by the C. I of t is the current flowing in the circuit, and V of t is the impressed voltage from the voltage source which powers the circuit. If we had just the inductor and a capacitor, the current would oscillate back and forth in simple harmonic motion, as we will see in the example. Introducing a resistor decays the oscillation and provides damping. In order to set up the differential equation for the circuit, we need to first define the voltage drop across each of the elements. For the resistor, the voltage drop is equal to the current I times the resistance of the resistor R. The voltage drop across the capacitor is equal to the charge on the capacitor Q divided by the capacitance C, while the voltage drop across the inductor is equal to the rate of change of the current in the inductor I prime times the inductance L. Thus, by Kirchhoff's laws, the voltage drop across all of the elements is equal to the voltage increase over the voltage source, which gives us this equation. Current is the rate of change of charge, so I is equal to dq dt. Using this, we can write the differential equation as a second-order differential equation for the charge Q. Let's consider a simple example of a circuit with just an inductor and a capacitor. The capacitor has an initial charge of 10 to the minus 6 coulombs and a capacitance of 0.25 times 10 to the minus 6 farads, while the inductor has an inductance of 1 Henry. Because there is no resistor or voltage, the differential equation simplifies to this. Using the values for the inductance and capacitance, we can define the equation in the Wolfram language. The initial conditions can be written here, since there is no initial current, meaning that Q prime is equal to 0 at t equals 0, but there is an initial charge of 10 to the minus 6 coulombs on the capacitor. Now that we have the equation and initial conditions defined, we can solve the equation using d-sol value. It is apparent from the solution that the current is oscillating due to the presence of just the cosine term in the solution. Let's visualize the flow of charge over time in the circuit. Because there is no resistance in the circuit, you can see that the current in the circuit oscillates and does not dampen. This is expected from the model and is analogous to an oscillating mass on a spring without air resistance. Second-order differential equations can be used to model many types of mechanical and electrical oscillations. Simple harmonic oscillations and the inclusion of air resistance and external forces can all be modeled by a single second-order linear non-homogeneous differential equation taking this form. Using the methods learned in prior lessons of this course, we can exactly solve questions of this type and thus draw conclusions about the behavior of a wide variety of physical systems.